You plug your phone into the wall, hear that little chirp, and walk away. But if you were to dive into those dark holes in the outlet, where exactly would you end up? You travel backward through the wiring in your walls, out to the neighborhood lines, and eventually merge onto a high-voltage superhighway. Those massive steel towers are carrying a river of energy from somewhere. For nearly a fifth of the United States, that river begins here. These windowless concrete slabs look static and silent, but they house a constant, invisible source of heat. The energy produced within these walls is the result of atoms being split apart, a process that generates enough heat to power your phone and entire cities simultaneously. The entire process starts with fuel, but it's not a liquid or a gas, it's solid. The fuel is made of uranium, baked into these little black cylinders called ceramic pellets. If we dive deep inside one of those pellets, down to the microscopic level, we find atoms of a specific type of uranium, called uranium-235. The center of this atom is a dense, vibrating cluster of particles waiting for a trigger. That trigger is a neutron. A single particle crashes into the uranium nucleus, instantly splitting it. This split releases heat and 3 loose neutrons. These neutrons crash into neighboring atoms, causing them to split and fire off more neutrons. One split causes 3, multiplying rapidly. There is a practical problem, though. When an atom splits, the new neutrons shoot out so incredibly fast that they tend to ricochet and miss the other uranium targets entirely. Engineers submerge the reactor in water to buffer and physically slow speeding neutrons, making it easier to hit the next atom. But this creates another issue. Unchecked, multiplying splits generate dangerous heat, so metal control rods slide into the water to act as barriers. These are called control rods. The metal alloy they are made from acts like a sponge for neutrons. By raising or lowering these rods, operators can absorb the flying particles to dial the heat up, turn it down, or shut the reaction off completely. Inside the reactor control room, engineers constantly monitor these temperature and reactivity levels. They watch walls of dials and screens to ensure everything stays balanced. By using water to encourage the atomic splits and control rods to limit them, the chaotic storm of splitting atoms becomes a steady, reliable furnace. This technical diagram shows the reactor. Ultimately, this advanced physics is just used to boil water. Inside the central vessel, pressurized hot water flows through a heat exchanger. It passes thermal energy to a second loop of water, instantly flashing into high-pressure steam. That steam blasts down a series of pipes until it hits a machine like this one. It physically pushes against the thousands of metal blades inside a massive turbine, forcing the central shaft to spin at thousands of revolutions per minute. Attached to that spinning shaft is the generator. Inside, a massive magnet whirls around giant coils of copper wire. That movement physically nudges the electrons in the wire, creating a steady stream of electricity that flows out toward the grid. A nuclear power plant functions as a massive atomic-powered steam engine designed to do one specific job: turn a giant metal crank. Once the steam has done its job spinning the turbine, it loses its pressure. To keep the cycle going, it has to be cooled back down into a liquid, so it can be pumped back to the heat exchanger and boiled all over again. That final cooling step happens inside these famous concrete structures. The towering, curved structures act as giant exhaust vents to release the leftover heat. People often look at the thick white clouds billowing out of the top and assume it's smoke or pollution. It is actually just pure, clean water vapor evaporating into the sky. Meanwhile, the newly generated electricity leaves the plant. It passes through transformers that step up the voltage, and it races out across miles of heavy transmission wire. It travels from the high-voltage towers, steps down into your neighborhood lines, flows through wiring in your walls, and finally meets your charger's prongs. The next time your screen lights up or you hear that charging ping, you know exactly what it took to make it happen. A microscopic atom of uranium was split in half miles away, sending a continuous pulse of energy all the way to your pocket.